Institute of Engineering and Technology.
Hello students, after defining function of one variable and two variable in the sense of derivative, today we are going to discuss how we can generalize all different concepts of derivative for function of one variable in case of multivariable functions. For example, how to deal with the total derivative. Now there is a concept known as total derivative in case of multivariable function, as in partial derivative we have seen that we are considering only change of one variable at a time. So how to deal with the total derivative of the function? Second case is how to generalize chain rule for function of two variables. Also we'll see how to go for the implicit derivative of the function. At last we'll see how to go for the multivariable derivative, that means partial derivative of higher order. So let us start with the first topic, that is total derivative in case of multivariable function. So if you look carefully, the definition of total derivative is like this. If I take a function f of xy and if I try to move from the point x0 y0 to the nearby point in the domain x0 plus dx y0 plus dy, then the total derivative is defined by this formula. It is denoted by df and it is defined by del f by del x into dx plus del f by del y into dy, where partial derivatives are considered at point x0 y0. So this is the definition which is known as total derivative. We will not go into the derivation of this definition at this particular point. You should remember this formula. Now let us consider this formula and remember it in a shorted form like this. It is f sub x dx plus f sub y dy and notation is df. If I take one example to understand this formula, by x square plus y square, then first order partial derivatives are del f by del x equal to 2x, del f by del y equal to 2y. And therefore, if I take all these inputs in my formula, it will give me df as 2x dx plus 2y dy. Now keeping this thing in our mind, as we are not considering any point at this stage, it gives me the general formula for the total derivative. Now if I focus on a particular movement from 1, 1 to 1.5, 1.5, and I can see clearly that the value in x and value in y, they are changing by 0.5 units respectively, and the original point is xy equal to 1, 1. Now again if I come to the formula which we derived, it is df equal to 2x dx plus 2y dy. I can see clearly by taking all inputs, it will result into final value which is equal to 2. Now what is the geometric interpretation of this final value? Remember, there are two things to be noticed at this point, which is the sign of the answer is positive and it is of 2 units. How to understand this whole thing means the total derivative graphically. If I construct the graph of x square plus y square, and if I fix the point in the domain which is 1, 1, 0, then the corresponding point on the surface is 1, 1, 2. Z is according to rule x square plus y square. And if I move from point 1, 1 to 1.5, 1.5 in my domain, then the corresponding point will move on surface like this. So this whole change is derived with help of total derivative. You can see clearly here the tangent or a part on which the point is moving on surface is denoted by yellow vector, which is obviously with the positive slope, and that slope if you count will be of 2 units. This is geometric interpretation for total derivative. These are the coordinates 1, 1, 0, 1.5, 1.5, 0. Starting point is 1, 1, 2 and ending point is 1.5, 1.5, 4.5. Now let us move to the second part, for multivariable functions, which is chain rule. How to generalize the concept of chain rule from function of one to function of two variables. So if I consider a situation like z is in terms of xy, x is in terms of t, y is in terms of t. So here I am taking interdependency in this order. Z is depending on xy, xy they are depending on t. So clearly we can see that there are two intermediate variables x and y, one dependent variable which is z, and only one independent variable which is t. To construct the formula for the chain rule, we need to consider branch diagram. So it is z equal to x comma y, x is in terms of t, y is in terms of t. So if I take z, z is clearly in form of x and y. So there are two branches of z. Z is depending on x, y. But x and y, they are now individually depending on t only. So remember this branch diagram to construct the formula. This is how we are considering formula for the chain rule in this case. Now here I can find only one possibility, which is dz by dt, as we have only one dependent variable z and only one independent variable t. And how many components will be there in addition into this formula, it is depending upon total number of intermediate variables. So here there are two intermediate variables x and y. So first component is exclusively for first intermediate variable x, and second component is exclusively for second intermediate variable y. So I can start by taking del z by del x. I am taking partial derivative y because z is at a time depending upon two variables. Whenever we have more than one variables, we should take partial derivative. But if we have only one free variable, we should take ordinary derivative. So I am taking del z by del x to move from z to x, and I am taking dx by dt to move from x to t. So this is whole idea, to move from z to t. Plus second component with respect to y. So it is del z by del y into dy by dt. So this is the formula for chain rule of z in terms of t, which is dz by dt. Now to understand this thing, let us consider one example. So z is given by x square plus y square, x is equal to t, y equal to t square. So you can look clearly here, I am using a color nodes to represent intermediate variable by purple, and to free variable I am using green color node, which is for t. So the branch diagram in this case is also exactly same. Z is depending on xy and xy they are depending on t, and this was our formula. Now for the first component we need two derivatives. First is del z by del x, which is equal to 2x. Here I am taking z equal to x square plus y square and differentiating it partially with respect to x, and second element is dx by dt, and for that I am taking x equal to t, differentiating it with respect to t, which will result into 1. Similarly for the second component I am taking z partially with respect to y, which is 2y, and y ordinary with respect to t, which is 2t. Considering all this in our formula, it will give me 2x into 1, 2y into 2t. But always remember, we should write our final answer in form of free variables. So I am converting all values of x and y in form of t. So x is replaced by t, y is replaced by t square. Simplifying this will give me final answer of dz by dt as 2t plus 4t cube. Now let us consider one more situation. Suppose z is depending on xy, but x is depending on rs, whereas y is depending on st. So in this situation we have branch diagram in this way. Z is depending on xy and x is depending on rs, y is depending on st. So we have one dependent variable z, two intermediate variables xy, and three free variables rs and t, and the distribution of variables is like this: z with two branch x and y individually with two branches, x with r and s, y with s and t. So this means now at this part we can find del z by del r, del z by del s, del z by del t. To construct the first partial derivative, let me take del z by del r. Now if you look carefully, to find del z by del r, I am focusing only on x, as this is the only intermediate variable which contains r. No need to consider component of y, as it is free from r. So in this case, focus only on intermediate variables which contains free variable r. So I am moving from z to x by del z by del x, and I am moving from x to r by del x by del r. Second case is del z by del s. I am moving from z to x and x to s, plus I am moving from z to y to s. Here I am taking two intermediate variables x and y because both of them contains free variable s. Finally, del z by del t, moving from z to y and y to t. So this is how we can construct partial derivatives, chain rule for multivariable function. So these are three possible cases in this situation. To understand the same situation, let me take one example. So z is given by x plus y, x is equal to r plus s, and y equal to s into t. So the first component del z by del r, it will be 1 into 1, because z is equal to x plus y, x equal to r plus s. So if I take partial derivative of z with respect to x, it is 1, partial derivative of x with respect to r is also 1. If I take second situation, del z by del x is 1, del x by del s is also 1, del z by del y is 1, and del y by del s is equal to t. So final answer is 1 plus t. And finally, del z by del t. So it is del z by del y, which is 1, and del y by del t, which is s. This is how you can find partial derivatives chain rule. These are only two situations. We can construct infinitely many situations by changing intermediate variables and changing free variables. Now let us move to the third part, which is implicit differentiation. Now if f of xy is equal to z and it is defining y implicitly in terms of x, then we can go for the implicit differentiation. So here I am taking df equal to 0, which means that del f by del x is dx plus del f by del y into dy. This is how we are defining total derivative. On the right hand side I am taking equal to 0, and then collecting the values of dy by dx, it will result into minus del f by del x upon del f by del y. Using the shorthand notation, it results into minus f sub x upon f sub y. To understand this topic, let us consider one example: x square minus y square minus sine of xy equal to 0, and we want to find dy by dx. So if I take f of xy equal to 0, my function will be x square minus y square minus sine xy equal to 0. Now the formula for the value of dy by dx using implicit differentiation is like this: minus f sub x upon f sub y. So I am taking in numerator partial derivative with respect to x and in denominator with respect to y. So ultimately it will give me answer for implicit derivative. Now let us go for the last case, which is higher ordered partial derivatives for multivariable function. For simplicity, if we consider only up to the second ordered partial derivative of function f of xy, this will give you the idea how to generalize the partial derivative for the higher order. Later on you can construct yourself third ordered, fourth ordered partial derivatives also. So the first case is f sub xx, that means second ordered partial derivative of f with respect to x and x. So you can see clearly the idea is almost clear and almost near to d square f upon dx square. But here I need to take partial derivative, so I am using del by del x. Similarly, f sub yy is del square f upon del y square. Now in this case be careful, as I am taking mixed ordered partial derivative. This is totally new concept for all of you. You have seen only and only in one direction, velocity and acceleration. This is how I am merging two different possibilities. So I am taking f sub xy. F sub xy is nothing but f sub x of y. So that means it is del by del y of del f by del x, and then combining this two, it gives me del square f upon del y del x. And in same way, f sub yx is del square f upon del x del y. Now the point to be noted at this particular part is, if I take shorthand notation f sub xy, and if I take the operator notation, the values of variables x and y are interchanging. You need to be careful about this thing. Now there is a theorem which is known as Feminist Theorem, which will help you in these two mixed order partial derivatives. It says that if we have first order partial derivatives f sub x and f sub y continuously defined on the domain of the function f, no need to find these two individually. You can find any one and it is exactly the same as all other mixed order partial derivatives. So let us consider one example to calculate this second order partial derivatives. So I am taking x cube plus y cube for simplicity. So if I take f sub xx, the first order partial derivative with respect to x is 3x square, and for the second order I am again differentiating it with respect to x, so answer is 6x. If I take f sub yy in the same way, it will give you answer 6y. Now if I take f sub xy, I need to take first partial derivative with respect to x, so it is 3x square, and then I am taking partial derivative with respect to y. So answer is 0, as my input is now independent of y. And here again, in the second case, you can see clearly f sub yx, it is again equal to 0 because del f by del y is 3y square and its partial derivative with respect to x is equal to 0. Now observe here, f sub xy and f sub yx both are resulting into same value, which is 0. This is happening because first order partial derivatives f sub x, which is 3x square, and f sub y, which is 3y square, they are continuously everywhere irrespective of the domain. They are continuous on the whole xy plane as they represents a polynomial. This is the reason why f sub xy and f sub yx are equal. So I hope all of you understand this mixed partial derivatives also. In upcoming lectures, we will see applications of partial derivative in case of multivariable function, like how to find tangent plane algebraically, how to construct the normal line for any point on the surface, what is known as gradient of the function, and will also add directional derivative. So I hope all of you are going through this lecture series, which is under the playlist of calculus. Please go through all lectures, so it will help you to move for the upcoming discussion. Thank you.
LJ Institute of Engineering and Technology.